I'd like to go into a little more detail about resistance. So recall that resistance is equal to rho L over A, where rho is the resistivity of the material, L is the length of the object, and A is the cross-sectional area. So let me sketch an object like so. And I'll just draw a box-shaped object. So it's going to have some length and some width and some height. So if I wanted to calculate the resistance of this object, well, let's say that I attach some potential difference between the two ends. So I'll attach one end here and one end here, and maybe I make those be at some potential difference, maybe a volt or 5 volts. Well, if that's the case, then the resistance of this object is going to be equal to the resistivity times the length, which is L in this case, divided by the area, which will be H times W. But let's say I hooked up the potential difference to the object differently. So I'll redraw the object. Okay, same object with the same dimensions, L, W, H. But let's say this time I attach the potential difference here and here. So let's say I have delta V from there to there. Okay, well then the area that I'm interested in is this area, and the length that I'm interested in is this length. Okay, so in this case, the R is going to be equal to rho times the length, which is just W, divided by the cross-sectional area, which is H times L. So as you can see, I get a totally different resistance in this case than I would get in the other case. It really depends on the dimensions of the object. All right, so when I said that resistance is a property of an object, even that's not quite true. It also depends on how we're using the object. So it really is something that can vary a lot depending on how we're thinking about it. Okay, so when I say that it's a property of an object, what do I have in mind? Well, there are actually devices that look kind of like this. So there's a wire, like so, and then a object kind of in the middle of the wire, kind of like this, and then another wire coming out of the other side. And this object has some resistance, okay, some known resistance, so we call it a resistor, because its most important property is its resistance. And there's an esoteric code that tells you what the resistance is. I'm not going to worry about it for this class, but you can look it up if you're interested. Just imagine that there are these colored stripes on here, and those colored stripes, if you know what you're looking at, can tell you what the resistance of this object is. So it has some constant resistance. That resistance doesn't depend on anything. And the place where you're connecting the delta V is obviously to these two wires. So you connect a delta V from somewhere over here to over here. And there's not really any ambiguity. You can't go sideways across this thing. All right, so what's the length of these? Well, it kind of depends. So this part, the little hot dog shaped piece, that's like probably less than a centimeter usually, so something like a centimeter. And then the wires can be whatever length, but the whole thing is a couple of inches long. Okay, so some objects like this will have a known resistance, and the resistance won't really depend on any other things. All right, so what that means is if I make a plot where I take delta V on one axis and I take the current on the other axis, if I just put different delta V's across the resistor, then what I'm going to get is a nice straight line like this. So different delta V's lead to some currents, and I get this. So for materials where this is the behavior, we say that they are ohmic. All right, so a resistor is a nice ohmic device. If I increase delta V, then I increase the current by a proportional amount. All right, not all materials have that property though. All right, so some materials, if I attach them like that and I increase the delta V, I get almost no increase in the current until some special point, and then it increases very rapidly. Okay, so if there's a behavior like this, then we say that's non-ohmic. And one example that would be similar to what I just drew is a diode. So diodes are semiconductor devices, and essentially up to some special potential difference, basically nothing happens. There's what we call a threshold voltage in order to start to see anything interesting happen. So for potential differences less than the threshold voltage, you see nothing. Once you reach that, then you get interesting behavior. Okay, that's also not the only kind of behavior. We could also have an object where if you turn up the delta V a little bit, then you get lots of current. But as you increase delta V more and more, you get less and less and less additional current for your work. All right, so this is also non-ohmic. And an example of an object that behaves like this is an incandescent bulb. And the physics behind this are, as the bulb heats up, its resistivity will change dramatically. So especially as it starts to glow, its material properties have become totally different than what they were when it was at room temperature. So for small potential differences, you can get a fairly big increase in current, but as you turn it up hotter and hotter, it's going to have different behaviors. So in general, resistivity is a function of temperature, and so when I say that the resistor has a constant resistance, that's really assuming that it's not getting super hot or anything like that. And then typically they will burn out if you get them to too high of a temperature. All right, so this sort of graph where we graph the potential difference versus the current is one way that we can characterize what an object does. Different objects will have totally different graphs. So we call this the IV characteristic curve. And typically it's actually plotted the other way, with the potential difference on the vertical axis and the current on the horizontal axis. I personally like doing it this way because this makes the cause-effect relationship clear. So the thing that I can choose is the potential difference, and then the current just happens. But there are standards and conventions and things. And so often the IV curve will be plotted the other way.